Hi, everyone. My name is Ami Choi. I'm a postdoc at the Center for Cosmology and Astroparticle Physics at The Ohio State University in Columbus, Ohio. Today, I'll tell you about cosmological lensing, focusing on recent results from the Dark Energy Survey. I will also put DES in context with some references to one of our sister surveys, the Kilodegree Survey, who recently put out some exciting new cosmology results. I'll conclude by briefly mentioning future prospects with upcoming surveys done with Euclid, the Rubin Observatory, and the Roman Space Telescope. I'll start with a motivation and background, tell you a bit of cosmic shear history, introduce the Dark Energy Survey, and present some recent results, and conclude with the path forward. A disclaimer is that I will not present any cosmological parameters from the Y3 lensing and clustering analysis. I will give you a glimpse of the data set and some preliminary measurements, and this will give you a primer for and hopefully even generate some excitement for what is to come. Starting with the background. We have this picture emerging of the evolution of our universe, starting from early times with the cosmic microwave background at redshift of 1100. And then structures form and evolve as the universe expands. And we can also see this through snapshots from n-body simulations, such as this one from the Illustrious simulation. And this is how the structures look at redshift 0, or today. And if you extrapolate the best fit CMB model to today, we have an energy budget that looks like this, using the cosmology coming from the Planck collaboration 2018. 68% of our universe is this mysterious dark energy. Another 27% is the mysterious dark matter, and only 5% is ordinary matter. There are different ways of observing the universe, and some of these measurements that we can make are sensitive primarily to geometry. These types of measurements include supernovae, baryon acoustic oscillations, and the CMB angular power spectrum. And there are further types of measurements that you can make that may have some sensitivity to geometry, but are telling us a lot more about structure growth. The main one that I will talk about today is gravitational lensing, but also galaxy cluster counts and redshift space distortions are very informative in this regime. If we look at a parameter plot where the matter density, or omega m, is on the x-axis and the dark energy density, omega lambda, is on the y-axis, 10 years ago it looked something like this, where what's shown are geometric probes only, thus the supernovae, BAO, and CMB. We've recently had an update to this, including the weak lensing and LSS information, large-scale structure information. And we have something that looks like this plot now on the right, which is covering just a small portion of the older plot. And here, these black contours now show the combination of the weak lensing coming out of the Dark Energy Survey, plus the large-scale structure clustering, plus the DES supernovae, and the DES photometric baryon acoustic oscillations. And the cool aspect of this is that all of these measurements are coming from within the same survey, the Dark Energy Survey. Since I'm going to focus mostly on gravitational lensing, I'll take a quick moment to review what that is. And we can look at this schematic on the right, where we have light traveling from very distant galaxies. And as the light travels from the source to us as the observer, it's passing by intervening mass structures. And these structures have mass, which therefore have gravity, which bends or distorts the path of the light as it travels to us. And so what we see on a two-dimensional projected image is something that looks like this bottom panel, where the light from the background galaxies is distorted in a particular way with respect to the positions of the lenses, or the structures that are causing the lensing. The two important ingredients in any lensing analysis include measurements of the source galaxy shapes and also the distances involved. So the redshift distributions, both between us and the lenses, the lensing structures, and between us and the sources that are being lensed. Cosmic shear is a colloquial term specifically to just meaning weak lensing by large-scale structure. The shapes of background galaxies are aligning with the foreground structure, and by measuring the correlation between pairs of ellipticities, you're sensitive to that large-scale structure. The cosmic shear is very commonly estimated using these two estimators, psi plus and psi minus, which are essentially telling us how aligned our galaxy pairs. And this plot comes from the DSY1 analysis from Troxel et al. So psi plus is on the top panel and psi minus is on the bottom panel, all as a function of angular separation on the sky. It might help a little bit to relate psi plus to the physics, so figure out what are we observing exactly and how do we connect that to the underlying physics. So psi plus can be written as an integral over something called the convergence power spectrum, and also a Bessel function. And this power spectrum in turn is related to some function Q, which is related to the survey window function, something about the depth of and the number counts of galaxies in that survey, and also P sub delta, which is the matter power spectrum, and this is where the cosmology comes in. The observables are then the measurements of the pairs of the correlation of pairs of shapes of galaxies, and also redshift distributions coming into this N of chi. And we can relate that to the cosmology, which comes into this matter power spectrum term. Lensing is specifically sensitive to omega matter and sigma 8, where sigma 8 is the normalization of the power spectrum on 8 H inverse megaparsec scales. And oftentimes you'll see a parameterization of this in terms of this capital S8, which is defined as follows here. Let's also consider two other types of large-scale structure correlation functions. The first is on the left here. This is something commonly known as galaxy-galaxy lensing. This is where background galaxy shapes align with foreground positions. And gamma T, so tangential shear or galaxy-galaxy lensing, takes a similar form as what we saw for psi plus, except there's a different Bessel function here. And it also picks up a factor of galaxy bias, because one of the quantities that we're doing the correlation with is a position. And positions of galaxies are biased tracers of the underlying matter density field. Similarly, we can consider clustering. This is the position-position correlation. And it also takes a form similar to what we saw for gamma T, and we often will denote it by W of theta. And here we have two factors of the galaxy bias, because now we're correlating two positions, and so they're both biased tracers of the underlying matter field. I'll move on to some cosmic shear history, and also want to note here that if I am citing people and you see their names in bold, this means that they are early career researchers. You can do a search on the astronomical data system. Specifically, I looked at the time period from 1999 to 2020 and required that all the papers be refereed and contain in the abstract the term cosmic shear, just to get a little sense of the timeline. The first detections of cosmic shear happened in the year 2000. So the field is, the measurement of it is only 20 years old. And there were actually 4 joint first detections, but one of the papers, Nick Kaiser's paper, didn't fully go through the refereeing process, so it doesn't show up in my search. And as we come to later times to point out some of these bubbles, this one here is the kilodegree survey 450 dataset. And these two, a little bit later, come from the dark energy survey year 1 dataset. We can look at this timeline in a slightly different way, just looking at galaxy surveys that are designed for cosmic shear. And again, the first detections of cosmic shear are here in 2000. And then there are a couple of ground-based surveys, the Deep Lens Survey and the Canada-France-Hawaii Telescope Lensing Survey, CFHT Lens, which took place in the early to mid 2000s. And now we're in this period where we're, two of these surveys, the Dark Energy Survey and the Kilodegree Survey, have finished or completed all of their observations, and we're still working on processing and analyzing the data. Hyper-C PrimeCam survey started a little bit later. They may still be taking some observations, but are set to complete fairly soon. And they've also had some cosmological results released already. Looking a little further afield, we have the Vera Rubin Observatory, which originally was slated to have its first light at the end of this year, but for COVID-related reasons, this has been pushed back a little bit. And then there is a legacy survey of space and time, LSST, which is slated to go on for 10 years. And also at sometime relatively soon, Euclid, one of the space missions, will launch and have its nominal 6-year mission. And finally, the Nancy G. Roman Space Telescope will launch, currently scheduled for the end of 2025. And one last comment here is that as we've evolved from these first detections of cosmic shear, the error on S8 has steadily decreased and the size of the teams have steadily increased. KIDS 1000 released their most recent cosmic shear results only a few weeks ago, and I highly encourage you to watch their webinar, which is linked down here. And this webinar concisely presents their findings. The plot on the left is from Marika Asghari's paper, which summarizes the cosmic shear analysis. And there are constraints shown here from their 3 different estimators for the cosmic shear. The 2 PCFs, that's the 2-point correlation functions, which I've already introduced you to. And there are 2 other estimators here, Kosebi's and band powers, which I won't talk about much, except I will come back to the Kosebi's. And there's about a 3 sigma difference between the Planck S8, which is extrapolated from the early time data from the CMB, and the KIDS cosmic shear estimation. The plot on the right is showing, again, the 3 different KIDS estimations at the top 3. And now there's also a comparison with some of the other ongoing and recent cosmic shear survey results, including DSY1, that's number 6 here, and HSC number 7. There's also a combination, well, there's first of all, the previous KIDS iteration, KV450, which is number 4, and then the combination of KV450 with the first year of DES data, which is this point. And you can generally see that all of these lensing surveys seem to agree. And maybe all of them may have a bit of an offset with the Planck data. Combining with the clustering and galaxy-galaxy lensing cross-correlations, the KIDS team obtains the cosmological constraints shown in this figure, and now we have omega matter on the x-axis and sigma 8 on the y-axis. Previously, I was showing you S8. Note that for this so-called 3x2 point, which is 3 2-point correlations, KIDS uses the anisotropic clustering signal from a spectroscopic survey from BOSS and 2DF lens. And so the results are a little bit different from what we used in DSY1 3x2 point, where the clustering information there came from an angular clustering, so 2-point angular function. And you can see that now the main result of this paper is lying kind of all of these results kind of seem to be going down some plane of degeneracy here. And I think the reported difference between the KIDS 1000 3x2 point and Planck results is something ranging between 2 and 3 sigma, depending on the tension metric that you use. And you can learn more by watching the parallel talks by Catherine, Benjamin, and Angus, and then attending the discussion for these results on August 27th. Now I'd like to tell you about the path going from pixels to cosmology, starting from when the light hits the detector. And you have, well, maybe before that you may have some atmospheric effects, and then you may have some detector effects. And we end up with imaging in different filters. There's some amount of imaging that you have a lot of over a wide area. And there may be some subset of this where you have much deeper exposure time, and so you can get much deeper data. From these images, you can build an object catalog with colors, and you can separate these objects into stars and galaxies. And the stars are very important here because we know that they should look like point sources. And if we model how not point-like they are, we can get a sense of what is the point spread function model. We also want to run simulations testing the process and how we measure the shapes and get some calibration information, and also run all of the catalogs through some null tests. And applying the calibration from there, we end up with a shape measurement catalog. So for DES, we have shapes for over 100 million galaxies. The other important ingredient that we require is knowledge of the redshift distributions for all of the sources. And usually it's beneficial to have overlapping spectroscopy, so you have some sort of knowledge of very good redshifts to compare against. And in photometric surveys, a lot of these distributions are measured using the photometry, which tend to be less accurate. And in cases like for DES, we don't have a lot of overlapping spectroscopy. And so we use some clever methods of getting around that, which I will come back to a little bit later. You can then measure your favorite statistic, for example, psi plus, psi minus, correlation functions. And then there's also the part where you build your theory model. And this involves maybe some input from n-body mocks, also some tests using synthetic data vectors, and then making method choices. What are the priors? What are the parameters to marginalize over? And the last very important ingredient is the covariance. And typically people will estimate the covariance, will calculate the covariance using an analytical prescription based on the Halo model. And then you can build your likelihood once you have your data and your model. And after running some sort of sampling analysis, you end up with cosmological parameters. It's a rather oversimplified flowchart, but it's to give you a sense of how we get from point A to point B. And while the details differ between the lensing surveys, the overall flow is probably roughly the same. And note that for DES, we have small to medium-sized teams working on essentially every box in this flowchart. And the complexity of the overall experiment has grown significantly, even from a few years ago. This leads me to some reflection questions for pertaining to science collaborations. And if this were a live talk, I would give a poll and try to get some information on what your thoughts are on this. And some of the questions I would ask would be, if you could design a utopian collaboration without any restriction, what would it look like? What would the structure look like? Would it be hierarchical or horizontal? And I think you could answer this question whether or not you're in a collaboration. And if you are in a collaboration, I would love to hear from you on what existing collaborations can learn from each other in terms of past successes and failures, specifically in improving equitable circumstances for underrepresented researchers. And if you're new to thinking about this, I highly recommend the resources given by the Particles for Justice team. And going back to what I worry about in terms of systematics from the weak lensing perspective, I'm going to roughly group these in terms of three types, although some of these are related and there's also overlap. So roughly astrophysical, analysis, and instrumentation and calibration. So for example, astrophysical uncertainties could involve not modeling the nonlinear matter power spectrum well. So not taking into account how baryons affect the matter power spectrum. There could be intrinsic alignments, also photo-Z errors and blending, and then some more analysis types of systematics in terms of the shape measurement algorithms. You can also have more instrumentation and calibration related systematics, including the PSF model and things that are happening in your detector that you may or may not be aware of, and also calibration and reduction issues. That's way too much to go over in one talk. I'll focus on a few of these. I will very briefly discuss the redshift distributions and reference some other talks that will take place in this conference. I will also briefly mention the modeling of the baryon physics, and I will talk about the modeling of the point spread function, and very briefly talk about detector system nonlinearities. Now moving on to recent results from the dark energy survey. Here are some photos of the instruments responsible for the science coming out of DES. No science is possible without the people, the Blanco telescope, and the dark energy camera. The dark energy survey is, when it's finished, will be 5,000 square degrees in GRIZY with a depth of around I of 24. The observing took 6.5 years to complete. There are more than 400 scientists involved. And there's a map here of the footprint of DES, which is in the southern hemisphere, showing the comparison between the area used for the science verification data, that's in red, that was 150 square degrees, and the catalogs are public. And then the last iteration of DES was all the data taken through the first year of observing, denoted as Y1, and that's 1,500 square degrees. This green hashed area, including also stripe 82 up here. The catalogs are also public for Y1. And we're currently here at Y3, where we've covered the full footprint, that's in blue, but we're only at half depth. So the Y6 dataset will be the full completed dataset to full depth. We measure galaxy shapes with the meta-calibration technique, which is described in the Y1 shear catalog paper, Zunz et al. 2018. And this is, meta-calibration is a shear measurement pipeline where the images of all the galaxies are distorted with a small known artificial shear. And then we calculate the response of the shear estimator. And here we use Gaussians fit to the 2D light profiles. And we have shapes now for greater than 100 million galaxies. The last point to make here is that we are still blinded, and there's a 3-step blinding process, which I'll summarize very briefly. I'm also going to attempt to use the word obscuration, since blinding is an ableist term, and it would be great if we could shift the community to different terminology. And this obscuration process involves 3 different steps. Firstly, the shapes are shifted by, or are scaled by some factor. And secondly, the data vector, or the 2-point correlation functions, also have some sort of obscuration. The process by which we apply that is described in Jesse Muir's paper, which I will refer you to for more details. And just note here that the shift does not degrade internal consistency tests. And the final aspect is that we also shift the parameter output when we make cosmology plots. We're doing a much better job at modeling the point spread function in Y3 compared to Y1. We're using a software developed primarily by Mike Jarvis, and this is called PIF, which stands for PSFs in the full field of view. And this does PSF modeling in sky coordinates, and there's a choice of modeling across a chip or over the full field of view. And there are also choices of different interpolation schemes. And you can then measure the shapes and sizes of the PSF model and data for reserve stars, where these are stars that we did not build the model of the PSF on. And they're being used for validating whether the model did a good job. We can then calculate the residuals between the data and the model in terms of either the shape or the size of stars. And then you can measure different correlations, either autocorrelations or cross correlations between the residuals for either size or shape of the stars, and also with the star sizes and shapes. And the idea is that these, if you get a signal, that would be an additive signal on top of the psi plus real space correlation function. And so you don't want a signal, you want as low of a signal as possible. And we see here that Y3 greatly improves on Y1. Y1 is the dashed line, Y3 is the solid line. And in all cases, we seem to be doing a great job of modeling the PSF. And this is just for qualitative reference, but the gray shaded region here indicates the smallest tomographic psi plus signal, which is in the lowest redshift bin. It's 10% of that signal. So you can see that the real signal is much larger than any of these systematics contributions that we see here. We can look at the shear catalog data in a different way. The cosmic shear field can be transformed to E and B modes, where for large-scale structure E and B modes, the E mode contains the cosmological info, and the B modes, if you have them, if they're not zero, that might indicate some systematics. We measured this using COSABIES, similar to what the kids team uses. COSABIES stands for the complete orthogonal sets of EB integrals, introduced by Schneider et al. 2010, and also described in several papers by Marika Asghari. And this estimator is designed specifically to cleanly separate E and B modes. And it takes as input the psi plus and psi minus real space correlation functions. So we plotted these on the right plot as data points, and also similar to the previous PSF plots, the gray shaded region is showing 10% of the expected E mode signal. And we see that the COSABIES data points are consistent with the null hypothesis that there are zero B modes. There's one additional B mode estimator that we used using pseudo CLs. These were computed with a public software called NAMaster, described in Alonso et al. 2019. And then we converted these pseudo CLs to COSABIES space. And that's plotted as this dashed line here. And so you can see, at least qualitatively, the two different B mode estimators agree fairly well, and they both seem to be consistent with zero B modes. So this is great news for our shape catalog. We can also look at preliminary obscured cosmic shear measurements. And you'll hear a little bit more about this in Alex Amon's talk. But I'll just quickly say here, there's measurements for the obscured catalog, and also this is dually obscured in the sense that the data vector is also has another obscuration parameter applied to it. These are shear correlations, psi plus and psi minus, binned in redshift. One is the lowest redshift bin, so this top panel is the lowest bin autocorrelated with itself. So the ellipticities, both from the lowest redshift bin. 4 indicates the highest redshift bin. And then you also have numerous cross correlations in between 1 and 4. And for the top plot, it's the same, but for psi minus. And for visual comparison, the Y1 error bars are shown as this shaded region. The total signal to noise is increasing by almost a factor of 2, going from Y1 to Y3. But that's not taking into account cutting any scales, which we may do for the final cosmology analysis. How are we treating redshifts in DSY3? The answer is carefully and differently than the way we treated them in Y1. The methods are described in this paper, which is already published, Brooks and Davis, 2019. And the general idea is that we're using an empirical method using self-organizing maps, or SOMs. And we put all of the wide field data into a self-organizing map. And what we're specifically putting in there is colors and fluxes. And then we're trying to link this map to the redshift distribution. And as an intermediate step, we also have a transfer function that links us to an SOM, which is constructed on the deep fields data. And these deep fields have many more filters than what we have in the wide field. So we have 8 bands, UGRIZ, JHK, and we build a transfer function taking us from the wide to the deep to the redshifts based on a software called Balrog. And this is basically a simulation where you can inject galaxies from the deep field and see what the selection properties are when you detect them in the wide field. I won't go into more depth into this because there will be a full talk about it by Giulia Giannini, and that will be discussed on August 27th. And I think also Alex Amon will talk a little bit about it on, in her talk, which will be discussed on September 1st. But the takeaway message here is that it's a very involved analysis now, and it's sophisticated enough to get its own flowchart, which I've intentionally made kind of small because it's just big enough so you can see that there are many different steps and there are people running different aspects of those steps. And you'll hear more about that. We're actually doing quite a bit more than 2-point correlation functions in DSY3. There's all kinds of interesting lensing and clustering science in progress, including mass maps and mass map-based statistics. And on the right, I'm showing you a figure made by Marco Gatti, which is a visualization of going from the science verification data, which is a small patch, to the year 1 results to the Y3 results. For more on mass maps, check out Andrew Bradshaw's talk, which will be discussed on August 26th. And also see plenaries by DES scientists Brian Nord on machine learning and cosmology, and Antonella Palmese on multi-messenger astrophysics. We are still learning from the DSY1 dataset, and I'd like to give you a few examples of that. In terms of galaxy clusters, we have this recent result from the beginning of this year where we have omega m versus sigma 8, and we see that the DS clusters cosmology seems to prefer a remarkably low omega m. And we found that the lensing inferred mass of the lowest richness clusters is 30% lower than expected. There are plenty of follow-up investigations changing aspects of the analysis, and one example is a recent paper by Maria Pereira investigates a new stellar mass proxy to calibrate the mass observable relation. And this paper is still based on the same cluster sample used in the main DS clusters analysis, but it does the binning. So this cluster analysis uses the richness of galaxy clusters, basically some number of counts, how many numbers of galaxies there are in the clusters, to bin the lensing signal. And for this paper, instead of using the richness, you can use the stellar mass proxy to do the binning. And therefore, it's not based as much on the red sequence. This plot from Maria's paper shows as a function of physical separation R, the lensing signal, or the 2D differential surface mass density on the y-axis. And these are for 3 different redshift bins, and also, so the lowest redshift bin is at the top, the highest redshift bin at the bottom, and the stellar mass bins are tend to be lower on the left and higher on the right. I also recommend Chun-Hao To's talk with a discussion on August 27th. He's done a lot of work in improving the understanding of projection effects for cluster analyses, and also methods for combining the cluster counts with 2-point correlations. And there's also some indication that maybe there's some aspect of a recent result or a phenomenon called lensing is low, which Alex Amon may refer to in her talk that will be discussed on September 1st. And for more on cluster systematics, I recommend checking out Yuanyuan Zhang's talk from an earlier installation of this conference, and here's the link for that. There's another area in which we're still learning from DSY1, and that's in the theory modeling of the nonlinear parts of the matter power spectrum, and specifically how baryons are affecting the matter power spectrum. And there's a paper by Hongjin Huang that builds a principal components model based on hydrosims to see if this model can accurately model the small scales of cosmic shear, which for the fiducial Y1 cosmology were simply thrown out of the analysis because we didn't think we could model them very well. So the idea behind this is that principal components analysis is a way of projecting data from a higher dimensional space to a lower dimensional space by maximizing the variance in each dimension. And here the PCA model is performed on the cosmological observables derived from a set of hydrosims, and these span some range of potential baryonic scenarios with different levels of feedback. The plot on the left is basically showing that for a synthetic data vector analysis where you know the truth, so S8, this black line here is the true value of S8. And then you can test different data vectors, either a dark matter only data vector, or a data vector contaminated by different baryonic scenarios. So either the illustrious simulation or the eagle simulation, where illustrious has stronger feedback and stronger impact from baryons. And then you can do things like apply the same cuts as in Y1 and see what you get back. So the cuts did a good enough job that you still recover the truth within error. Now, if you instead use this model and include the small scales and do the analysis, you see that if you don't marginalize over any parameters of that model, you're getting a biased result if the feedback is similar to what is in illustrious. If you then marginalize over parameters of this PCA model, if you marginalize over 1, you seem to recover an accurate S8 accurately at the expense of having larger error bars. And then going to 2 modes marginalized, then you increase your error bars further, and there's not a whole lot more gain. And so for Y1, Huang et al. Finds that marginalizing over 1 mode is enough for the statistical errors of Y1 to recover this unbiased result. And here's the result for omega matter versus S8 for the 3x2 point shear, with the shear going to including the smaller scales that were thrown out of the Y1 analysis. And this parameter Q, that's the first PC mode, and it's been given an uninformative prior, and so it calibrates itself. And then for comparison, you can see the Planck data, and here note that this is polarization only, plus BAO, and then the red contour here is the combination of DES plus Planck. So this is a potentially exciting way of dealing with the baryon systematics for the future. Stay tuned for DSY3 Lensing Cosmology. It's underway. We'll be excited to compare with results from kids and HSC. And I think we're learning a lot still from Y1, and that will be true also for Y3 in the next several years as we approach the next generation of lensing experiments. Speaking of which, if we look back at the Galaxy surveys timeline, again, we have Rubin, Euclid, and Roman. And I won't really have time to talk about it much, but one of the really exciting areas is that we'll be doing a lot of cross correlations and co-analyses of these different missions. And that will help not only for improving cosmological constraints, but also for mitigating systematics. And additionally, you can cross-correlate these surveys with all kinds of other experiments coming from the 21 centimeter, CMB, spectroscopic surveys, you name it. A little bit about the Roman Space Telescope, formerly known as the W1st Space Telescope, infrared space telescope. Roman will investigate the origin of cosmic acceleration, and the planned launch is at the end of 2025. It's a Hubble-sized telescope with a similar power and resolution, but with 100 times the field of view. And you can see here on the lower left, a simulated observation of M31. There are 18 infrared detectors across this focal plane. And because this mission will be so powerful statistically, we'll need to very carefully figure out any potential systematics. And in particular, that means vetting these detectors carefully to do a lensing analysis. And we can do that using laboratory flats and darks for prototype and candidate flight detectors. And these come from the Goddard's Detector Characterization Lab. So there's a group of us at Ohio State who have been making measurements of nonlinearities for candidate flight detectors. And this is an example of that. And basically what's being measured here is the nonlinearity in the detector. And we're also getting quantum yield and charge diffusion characterization. And this is a project led by Jamora Givens. One of the steps is to plug what we're finding out about these detectors into image simulation efforts to determine cosmological impact. And this is a picture from the Roman image simulations paper recently written by Troxel and Long et al. Finally, we have plenty more detector data to analyze, including other flight candidates for Roman, and our methods are also applicable to other space telescopes such as Webb and Euclid. I'm now to my summary. I started with the landscape of cosmic shear surveys, and this is the latest and greatest lensing results from the KIDS 1000 team. And we see that there still seems to be some sort of 2 to 3 sigma offset between what the KIDS data are telling us and what the Planck early time universe is telling us. We're making a lot of progress for the Y3, for the DSY3 cosmic shear and large-scale structure analysis. And I've shown you that our catalog doesn't seem to exhibit any sign of systematics. And we even have our first obscured data vectors. I also told you a little bit about things that we're doing for ahead of the Roman Space Telescope launch. And finally, we've faced a lot of unique challenges this year. And I'm eager to have many more conversations perhaps in the discussion for this talk, about what a healthy, diverse, equitable collaboration looks like, and how we can build these as we leverage this health to do better science and figure out the universe we live in. And the last comment is that DSY3 will not be the 2.0 version of Y1 because we've vastly refined our methods for systematics control. And combined with 100 million galaxies, I think we're in for some excitement. Thank you very much for listening.